Bro,
So I
finish.
think the recording, okay, the recording has started. Okay, so um, so good evening, everyone. Today, we are going to discuss a topic
Bro,
on DA assignment. Hello, yeah,
bro, share
hello.
the screen now. Screen
Oh,
is not
this.
visible.
Okay, I haven't shared the screen. Okay,
Yeah, bro.
let me share it. Okay, share content. Screen. I think you can see my desktop. Hello, you can
Uh,
see my desktop screen now.
yeah, now.
Yes, yes.
Now it's visible.
Okay. I'm opening the presentation. Okay, so now you can see the presentation as well.
Yeah, yeah.
Okay,
No. Presentation
it's
is
still
not
not.
visible. Yeah, now
Why?
it's visible.
Now it's visible
Yeah,
now.
yeah, yeah.
Yeah,
It's visible now.
Now it's
you can.
visible.
That black background. Okay.
Yeah.
Yeah. Okay. So I can start now.
Yeah, you can start.
Okay. So good evening, everyone. Today we are going to discuss a topic for DA assignment, that is 0 by 1 knapsack problem using dynamic programming. Well, today the presentation is being presented by myself, Anirban Mall, my friend Aniket Chetri, and Yashwan Basnet. Well, so I would first of all like to introduce the topic. What is knapsack problem? Well, knapsack problem is a kind of problem, or we can say an algorithm in DAA, where we are provided with a set of values and a set of weight, and we have been assigned with a particular value for a particular weight. We have been assigned with a particular value along with a weight, and we have been given a limit for a weight, and we need to add, or we need to apply the summation for the weights, and equivalent to that the values will get added as well. And the main motto is that we need to sort out, or we need to extract out the maximum value out of the weights, but the summation of the total weights must not exceed the target value, or the limit of target value of the weight, or the limit of the weight. So this is how we solve a knapsack problem, and this is a genuine knapsack problem. And what makes it different from 0 by 1 knapsack problem is that we have to use a weight as a whole. We cannot partialize a weight. Suppose the weight is 10, then we cannot break that weight into parts of 5 and 5 or 7 or 3. We have to either use the entire weight of 10, or we need to ignore it, but we have to use it as a whole. We cannot break it. This is what we call 0 by 1 knapsack problem. So as it has been said that the knapsack problem is a problem in combinatorial optimization. Given a set of items, each with a weight and a value, determines the number of each item to include in a collection, so that the total weight is less than or equal to a given limit, and the total value is as large as possible. It actually derives its name from the problem faced by someone who is constrained by a fixed size knapsack and must fill it with the most valuable items. The problem often arises in resource allocation, where the decision makers have to choose from a set of non-divisible projects or tasks under a fixed budget or time constraint, respectively. A 0 by 1 knapsack problem is similar to a genuine one, but the only difference, which I said right now, is that in this case, the item cannot be broken, which means we should take the item either as a whole, or we need to ignore it. This is what we actually call a 0 by 1 knapsack problem. Each item is being taken or not taken. It cannot be a fractional amount of an item taken an item more than once. And yes, one more point: we cannot take a particular item or a weight more than once. We can either use it once, or we need to ignore it. So the entire explanation in a form and example is that the given the weights and values of n items, we need to put these items in a knapsack of capacity W to get the maximum total value in the knapsack. In other words, given two integer arrays, a particular array which has been given value with the items being from 0 to n minus 1, and another array weight which also contains items from 0 to n minus 1, which represents values and weights associated with n items respectively. Also, we need to give an integer w, which represents knapsack capacity, and find out the maximum value, that which is the subset of val, such that the sum of the weights of this subset is smaller than or equal to w. We actually cannot break an item. Either we need to pick the complete item or do not pick it, as the property of 0 by 1 knapsack problem tells us. Here is an example to prove it. There is a set of values which is 60, 100, and 120, and there are another set of values for an array called weight, which is 10, 20, or 30, and the maximum limit of weight is 50. So here are different methods to find out the maximum. Here are different methods to take out the or extract the maximum value out of these weights. Number one is weight is 10 and value is 60. Means the weight and values have been given here. Weight is 10, value is 60 for that weight. Weight is 20, then the value is 100. If the weight is 30, then the value is 120. Weight, so first of all, we would like to try by taking two weights, 10 and 20. So if we take out the sum of weight 10 and 20, then it will be 30, and the total value will be 160. Another example, which is so the total weight here is 30, which is actually less than 50. Hello, and yes, then the next set of values are 30 and 10, which will summarize up to 40, which will still be less than 50, and the value extracted is 180, that is 120 plus 60. And another final example is 30 plus 20, which is equivalent to 50, which is correct because we can take the maximum value either which is equivalent to the target value or needs to be less than that, or at most equivalent to that. So the weight would be 30 and 20. We would if we would take out the sum of both these weights, then it will be 50, which is valid, and the total value extracted is 220. That is 120 plus 100, which is 220 eventually. So the ultimately and there is one final case where we can take 30, 20, and 10, but the problem is that it will summarize up to 60, which is more than 50, so it's not valid. So ultimately, the solution of this problem would be 220. And remember that we can use a weight only once. This is what 0 by 1 knapsack problem is all about. And so here are different methods to actually solve a 0 by 1 knapsack problem. So now I would like to call upon my friend Aniket to carry on the proceedings from here. Aniket, you can continue from here onwards.
Thank you. Thank you. I'll be talking about the knapsack problem to be solved by the recursion by brute force algorithm or exhaustive search. So the approach will be to solve a solution consisting of all the subsets of items and calculate the total weight and value of all subsets. So we'll consider only the subsets whose weight is smaller than W. From all subsets, pick the maximum value subset. So there will be two optimal subset structure. The cases will be two. So the first case is the item is included in the optimal subset, and case 2 will be the item is not included in the optimal subset. Therefore, the maximum value that can be obtained from n items is the max of the following two values. So the following two values are maximum value obtained by n-1 items and W weight, excluding the n term, and the second one is value of n term plus maximum value obtained by n-1 items and W minus the weight of the nth item, which will be including the nth item. If the weight of the nth item is greater than W, then the nth item cannot be included, and the case 1 is the only possibility. So here we have a example which my friend Anirban has already explained. I guess the output of the code will be 220. I think he already explained. So now I'll be like to call Yashwant Basnet for the further explanation. Yashwant, please take over.
All right. Thank you, Aniket. Anirban, can you just check your screen? It's a bit blurry, I think.
Uh, Is there any technical problem? Because I think it's okay. It's still blurry because of the
No,
network
no,
issue
no,
or something. Okay,
no,
it's
it's not okay.
perfect now.
So, yeah, yeah.
Okay, yeah, bro. You can continue. Yeah.
Okay, so now I would like to talk about the other method, which is the method using dynamic programming. We'll be using dynamic programming to solve the 0-1 knapsack problem. So like other typical dynamic programming problems, recomputation of same sub-problems can be avoided by constructing a temporary array that is key, or you can say that we can create a matrix in bottom-up manner. So the following is the dynamic programming based implementation. So the approach is simple. In the dynamic programming, what we'll do is we will work considering the same cases as mentioned in the recursive approach, like Aniket said. So what we'll do is we'll consider a dynamic programming table and all the possible weights from 1 to W as the columns, and the weights that can be kept as the rows. So the state dp I and j, which are I will consider the number of rows and j will consider the number of columns, will denote the maximum value of j weight considering all the values from 1 to ith. So if we consider wi, that is weight in ith row, we can fill it in all columns. We have weight of values is greater than W of I. Now two possibilities can take place from here. First is fill W of I in the given column, or do not fill W of I in the given column. So now we have to take a maximum of these two possibilities. Formally, if we do not fill ith weight in jth column, then dp of I and j state will be same as dp of I minus 1 of j. But if we fill the weight, then the dp of ij will be equal to the value of w of I plus value of the column weighing j minus w of I in the previous row. So what we'll do is we'll take the maximum of these two possibilities to fill the current state. So now let us see what we have just explained through visualization to make the concept more clear. So here we have a list containing the weight of the elements. We have three members in the list, and we also have the values of the list as well as the capacity, which is given as 6. Now what we have done is we have created a matrix where the columns where we have named the columns as from 0 to 6, which is the capacity, that is equal to 6. So we have just given the columns as 0, 1, 2, 3, 4, 5, 6. And in the row section, what we have done is we have given it from 0 to 3. That is, we have three members containing in the list. So we have just given as 0, 1, 2, 3. And now as for how we are adding the values in the matrix, so we have the explanation down there. So for filling weight is equals to 2, so we come across j equals to 3, in which we take the maximum of what is there is 10 or 15 plus dp of 1 which is the the row ith row, and for the column we'll have 3 minus 2, which is equals to 25. So now we have for between 10 and 25 is the maximum, so we will take we'll take the 25 value, the maximum value. Just like that we have filled in, and down there we also have explanations for other fillings, like if weight equals to 3, then we come across j equals to 4, in which we will take the maximum of 25 and 4 plus dp of 2 and 4 minus 3, which is I think 50. So we will take the 50 as the maximum, since it is maximum between 25 and 50. And then we also have for weight equals to 3, we will come across j equals to 5, and then we will also take the maximum from there, which is 55. And then for weight equals to 3 and j equals to 5, we'll take the maximum from there, which is 65. So now this is the approach for using dynamic programming. Let us see this through a program that we have down below. Anirban?
Yeah. Hello.
Below, yeah, okay. So this is a problem for
Any problem?
calculating
Yeah.
for solving the knapsack problem using dynamic programming, just a simple Python program. What we have is here is just a simple program, knapsack, and then the weight and values, and n as for the number of list, and then just a simple program. We'll have a for loop for n plus 1 and W loop for W plus 1, as we, like I said in the previous section, the matrix, and then just a bit of programming. The approach is same, like the calculations are same as I've shown in above. So just like that, this is a simple approach. Now and the output we also get as 220, as Anirban and Aniket said in their previous methods. So now I would like to ask Anirban to take over from here and discuss the other method that we have. Thank you.
Okay, thank you, Yashwant. So now we are only left with the last method, which is the method tree, and this method uses memoization technique. It is actually an extension of recursive approach. This method is basically an extension to the recursive approach, so which is actually the method one, so that we can overcome the problem of calculating redundant cases and thus increase the complexity. We can solve this problem by simply creating a 2D array that can store a particular state n comma w if we get it the first time. Now if we come across the same state n comma w again, instead of calculating it in exponential complexity, we can directly return its result stored in the table in constant time. This method gives an edge over the recursive approach in this aspect. Means it's ultimately trying to say that this method 3 is better than the method 1. So here is a small Python program to show the implementation of the above approach, and it's a small Python program. Here we have first of all provided a driver code with values assigned to val, and means the values assigned to the array weight, and the target value is 50, and the length of val has been assigned to n. Then we initialize the matrix with -1 at first. Then we assign a certain value, -1 for I in range w plus 1, for j in range n plus 1 to t. Then we define a function knapsack with certain variables within it, such as weight, val, w, and n. Then we provide a base condition if n is equal to 0 or w is equal to 0, then return 0. Else if t n w is not equal to -1, then we return the value t n w. Then we have a choice diagram code. If w t n minus 1 is less than equal to w, then t n w is equal to maximum of val n minus 1 plus knapsack weight val w minus w t n minus 1 and n minus 1. And there's another value knapsack wt val w and n minus 1. Therefore, it will return the maximum out of it. The t and w will actually return the maximum out of the both values, and so it will return the maximum value. And else if the weight n minus 1 is greater than w, then t and w is equal to knapsack weight val w n minus 1, which will ultimately return t and w as well. And ultimately, we will print the function knapsack with attributes such as weight, val, w, and n. So ultimately, we will get the output of 220 as similar to the method 1 and method 2. So ultimately, we have come to the end of this presentation. I would like to show the references as well from where we have got our content. Here I have provided 4 links as reference for whatever content I have shown. And thank you all of you for listening to us. I guess we all have provided you with enough content which will be beneficiary for all of you guys. Thank you. I can stop the recording now, guys. Hello.
Yeah, you can stop.
Okay, now I can stop.
Yeah.
Stop recording. The meeting is being recorded. I should want to stop recording.